In this lesson, we're going to look at quantum theory, one of the weirdest ideas that have ever been developed in science. In the last couple of lessons, we looked at Einstein's theories of relativity, and those dealt with the universe on the largest scales, scales much, 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 much larger than the ones we're familiar with. And what we saw is that when you actually study the universe at those large scales, it turns out that things are very, very different than what they appear to us, sort of in the middle of the universe. In this lesson, we're going to shift to the other end of the scale, and we're going to look at what we discover about the nature of reality when we look at the universe on the smallest scales, the level below atoms, the subatomic world. Previously, we had talked about the idea that light is a form of electromagnetic radiation, and that electromagnetic radiation is pure energy that travels through empty space in the form of waves of electrical and magnetic fields. And that was important because we said that looking at understanding that light can be thought of as a wave means that we can apply what we learned from studying other kinds of waves to an understanding of light, and that gave us some real insights. But we didn't talk anything about the proof that light is a wave, because in fact there is another possibility that has been suggested, and that's that light actually propagates as a series of tiny, tiny, tiny little particles. This was called the corpuscular theory of light, and in fact had its supporters. Among them was Isaac Newton. Now, these two theories seem to be utterly incompatible. Particles and waves are two very, very different things. Particles are bits of matter and therefore are described by mass. Particles are localized, meaning they're found in one particular spot in space. You can point at a particle and say it's there. Waves, on the other hand, are not really things, they're motions. And as motions, they don't have mass. You know, what is the weight of a motion? They're described by wavelength, and they're delocalized. They're spread over a large region of space. Where point to this wave from this cute little kitty, and it's kind of spread out over this whole area of space that is encompassed by the entire motion. So particles and waves are completely different things, which means when Einstein and Newton and other natural philosophers in his day were arguing about whether light is a particle or light is a wave, they were offering very different and incompatible pictures of light. Well, as we know, the wave theory of light won out. Why was that? Well, there was a lot of observational evidence for the wave nature of light. Light does things that we typically associate with waves. It spreads out, what we call diffraction. It bends, what we call refraction. And so there was a lot of evidence. The final settlement of the issue seemed to be an experiment by an English physicist, Thomas Young, around 1801, famous double slit experiment, because what he did was he shone light through two narrow slits. Now, remember the two most important words in science, the deductive reasoning, if and then, and we make a prediction. So if light is a series of particles passing through these slits, what would you expect to see? You'd expect to see the particles, any particles that don't go to the slit will bounce off and be reflected back. Any particles that go through the slit will travel through and hit the detector screen behind. And what you'd expect to see then are two regions of light and nothing else. But in fact, when this experiment was done, this is what was observed. It was not two individual regions, bright regions, and the rest darkness. There were actually these alternating bands of brightness and darkness and brightness and darkness. This is what's called an interference pattern, and it's absolutely classic of waves, because what happens is that as the two waves come through these slits, they spread out, and as they spread out, they run into each other, and in some places, they reinforce each other. As both waves are going up, they push each other up even higher, and you get a very, very bright region. In other places, where one wave is going up and the other wave is going down, they actually cancel each other out, and that's why you get these dark regions. And so this is absolutely characteristic of waves. Light demonstrates this interference pattern, and therefore we can conclude that light is a wave. There is also a lot of theoretical evidence for the wave nature of light. A Scottish physicist, James Clerk Maxwell, in the 1860s, came up with a whole set of equations that actually gave us the idea of electromagnetic radiation. Radiation just means to spread out in all directions. And he showed in studies of electricity and magnetism, his own and other earlier scientists, that in fact what we see as light is actually the propagation of electrical and magnetic fields spreading out as waves throughout space. And the mathematics of this work perfectly to describe all sorts of phenomena of light, including, as we saw, predicting the speed of light that led Einstein to develop general relativity. And so at this point, it seemed pretty clear to everybody that light is indeed a wave. It spreads through space as a wave. But there were still some problems, a few little observations that couldn't really be explained very well by treating electromagnetic radiation or light as waves, and that's what we'll look at in the next video.